Hello there. In this lesson, we will begin our investigation into complex numbers. Complex numbers is divided into two topics, the introduction and using complex numbers. In this lesson, we will begin looking at N1.1, Arithmetic of complex numbers. In particular, we will look at using the complex number system. In this lesson, we will first look at real numbers and imaginary numbers, and those two come together to form the complex number system. Then we will look at the number I in more depth and begin to look at equations using the number I and imaginary numbers. Before we begin the content, I think it's important to start off with an introduction into the complex numbers. Complex numbers were first used in the 1500s when mathematicians Girolamo Cardano and Niccolo Tartaglia were trying to solve quadratic and higher-order polynomial equations. They in particular had an interest in ballistic flight, also known as projectile motion. They noticed that some equations were easy to factorize and solve. Others required the square roots of negative numbers. We now know from the quadratic formula that those equations which cannot be solved using real numbers have a discriminant less than 0. The mathematicians knew that it was impossible for a negative number to have a square root, because no number, when multiplied by itself, is negative. Therefore, no real number squared can be -1. Nonetheless, Cardano began to use the square root of -1 in his solutions, albeit hesitantly. Remarkably, this imaginary number was used to find solutions to his real number problems. Like Cardano, by the end of this lesson, we will be able to do the same thing and find the imaginary solutions to real quadratic equations. Soon we'll get into the difference between imaginary and real numbers. In every lesson, I will look to provide the purpose and applications of what we are using to the real world. So the term imaginary numbers is actually quite misleading because they have very real-life applications. Imaginary numbers help define complex numbers, which have large impacts on our study of the physical world. You would have practiced addition of ordinates of different functions in Year 11. One example you might have done was the addition of trigonometric functions. And while this initially didn't seem too hard, you might consider that if the functions are out of phase, this process will become much more difficult. In this case, complex numbers are used to resolve the issue. For instance, physicists use complex numbers to calculate the combination of alternating current sinusoidal waves in electricity. Another application, which those studying physics will glance over in the HSC course, is Schrödinger's equation. This is used to predict the behavior of a wave in quantum mechanics and is rooted in complex numbers. A third case is simply finding all the solutions to polynomial equations. This is what we will begin doing. This is useful for modeling the motion of a projectile or in financial areas, such as determining the profit of a product. In the description, I will attach some websites and videos which go into more depth on the discovery and applications of complex numbers. Now the difficulty rating. The introduction to complex numbers topic on a whole is not too difficult at a 6.5 out of 10 on my scale. The content of this lesson, use the complex number system, I would put as a 4 out of 10. Really, the only difficult part is to wrap your head around the new concept of the imaginary numbers and the imaginary unit I. The first part is to develop an understanding of the classification of numbers and their associated properties, symbols, and representations. To do this, we will begin looking at a number diagram. You will be familiar with this, so we begin with the natural numbers. And they are indicated by the N with a dash. Then we move out into the integers. And they are signified by the Z. And then we've got the rational numbers. And the irrational numbers. Rational numbers are indicated by Q. The rational and irrational numbers come together to form the set of real numbers. They are represented by the R with the dash. We can say that real numbers are represented by the pronumeral A. Up until now, all of your maths has been involved in the real numbers. But there's a whole nother side of mathematics which we have not yet explored. If we expand this out, we will find another set of numbers. These numbers are the imaginary numbers. And they consist of the same subsets as the irrational and the rational. And the rational is broken up into the integers and the natural numbers. This is just the same as the real numbers. The imaginary numbers are indicated as BI. B is any real number, and I is the imaginary unit, which we will get into soon. Together, the real and imaginary numbers come to form the set of complex numbers. Now we will do some refreshing questions on classifying numbers. Feel free to pause the video here and complete the question yourself, or else follow along with me. The number 1, this is a real number, but it can be broken down further if we look here. The number 1 is rational. It is an integer. The base, it is a natural number. -7/2. Well, it is not a natural number because it is negative, and also because it is not a whole number. It is not an integer because it's not a whole number, but it is rational because it can be written as a fraction. Next we have I. I is an imaginary number. And if we just go back, we said all imaginary numbers are in the form bi. In this case, b is equal to 1. 4 plus 3i. This is in the form of a complex number. E, we have pi. Pi is irrational. Another term which we can use to describe pi and e and other numbers like them is transcendental. And finally, we've got 0.3 repeater. This can be written as a fraction, so it is a rational number. The next part of the syllabus is to define the number I. I is the imaginary unit. The syllabus defines I by the equation I squared equals -1. In other words, I is a root of the equation x squared equals -1. The other root would be -I. We can just quickly verify this by the factor theorem. If we go I squared, we know that that is equal to -1. And if we go -I squared is equal to -1 squared times I squared, which is equal to 1 times I squared is equal to -1. So given that I is a solution to x squared equals -1, it is also a solution to the quadratic equation x squared plus 1 equals 0. But if we graph this, we will have the y-intercept at 1, and it will be a parabola, something like that. But notice how there is no x-intercept to this equation. Well, this is because there is no real solution to the equation x squared plus 1 equals 0. And since the Cartesian plane is purely real, we cannot graphically observe this imaginary solution. Another important thing to define with the imaginary numbers is that they are immeasurable. While we can represent real numbers as an ordered pair on the number line, this is not the case with imaginary numbers. In other words, we cannot represent them using the greater than or less than notation. It also means that they are neither positive nor negative. Now, we can do arithmetic with imaginary numbers just like we do with real numbers. We will just treat the imaginary unit as a pronumeral. So let's just go through these questions. We've got 1 plus 5i, pretty easy, we've just 6i. Now we've got 5i minus 7i, and just treating it like normal arithmetic, we've got negative 2i. C is a bit more tricky. We've got I times I, that's I squared, and back to our definition up here, that's equal to negative 1. Now we've got D, 5i squared divided by 5i, so we can cancel the 5's and cancel one of the i's, so that's just equal to I. E, the square root of negative 3. So how would you do this? Well, we can write this as the square root of 3 times the square root of negative 1, but the square root of negative 1 is a solution as I, so this is equal to root 3i. F is similar. We've got a root of negative 7, so we can write this as root 7 times root of negative 1 plus 5i, which is equal to root 7i plus 5i, which is equal to 5 plus root 7i. Question 3 is a bit more tricky. We're going to use the concept of I to factorize and solve the following equations. So x squared plus 4. Previously, we wouldn't be able to factorize this expression, but now with our knowledge of I, we can say that 4 is equal to negative 4i squared, since I squared is negative 1. So let's write this as x squared minus 4i squared is equal to 0. Now we can do a difference of squares. So x minus 2i, x plus 2i equals 0. So we get our two solutions, x equals 2i and negative 2i. And now b, x squared plus 1 equals 0. Well, this is just a rewritten of the equation x squared equals negative 1. But we can do the same thing. We can say that 1 is equal to negative I squared. So therefore we can get x squared minus I squared equals 0. So x minus I, x plus I equals 0. Therefore x equals I or negative I. Now the third part is to use the symbol to solve quadratic equations that do not have real roots. Well, now that we've defined the imaginary unit, we can go back to work which we have done in younger years involving quadratic equations. So let's look at this equation. We've got x squared plus 5x plus 6. Now remember, there are many methods we can use to solve this equation. We can factorize, we can use the binomial theorem, complete the square, we can do a graphical solution, we could even do the factor theorem when the remainder equals 0. For this one, I'll choose to factorize. Well, which two numbers will multiply to 6 and add to 5? Oh, we've got x plus 3 and x plus 2 equals 0. So therefore our two solutions will be x equals -2 and x equals -3. Now if you wish, you could sub those back into the equation and verify the answer. Notice that we get two solutions. This makes sense with respect to the fundamental theorem of algebra. You may remember this theorem. It states that every non-zero, single variable degree n polynomial with complex coefficients has exactly n complex roots. Put more simply, a polynomial with degree 2 will have 2 roots. This is satisfied in this equation. Recall that we can use the discriminant to determine how many real roots we will get. This is shown by discriminant equals b squared minus 4ac. In this case, a is 1, c is 6, and b is 5. So we'll get 5 squared minus 4 times 1 times 6 is equal to 1, which is greater than 0. Therefore, we will get 2 real roots. Let's move on to this next equation. X squared plus 2x plus 1. Again, this is pretty easy to factorize. We just know it's a perfect square. X plus 1 squared equals 0. X equals -1. Again, looking at the fundamental theorem of algebra, there should be 2 roots. In this case, the root x equals -1 is a double root. This would be shown that if we solve for the root of the derivative, we will get the same, x equals -1. Therefore, the theorem is satisfied. But again, let's check with the discriminant. So discriminant b squared minus 4ac, which is equal to 2 squared minus 4 times 1 times 1, which is equal to 0. And remember, if we get the discriminant equals 0, we will get one unique solution. This was shown here. The next case, x squared plus 2x plus 9 equals 0. This one isn't so easy to factorize, so let's go to the quadratic formula. Recall the quadratic formula. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. Now let's plug all our values in. We get -2 plus or minus the square root of 2 squared minus 4 times 3, 4 times 9 times 1, all over 2 times 1. And checking that, we get -2 plus or minus the square root of 2 squared minus 4 times 9 times 1, -32 over 2. Now this is a problem. How are we going to resolve this? Well, now that we know complex numbers, we can do the same as what we've done before. Let's continue up here. We can write this as -2 plus or minus root of 32 times root of -1, which is equal to -2 plus or minus 4 root 2 I over 2, which is equal to -1 plus or minus 2 root 2i. So we've now found the complex solutions to this quadratic equation. Again, this satisfies the fundamental theorem of algebra as we've got the 2 solutions. Let's again look at the discriminant. Discriminant equals b squared minus 4ac, and that was equal to -32, which is less than 0. Remember, in younger years you learnt that when the discriminant is less than 0, we get 0 real solutions. And this was shown here, where we got complex solutions. Let's do the same thing in D. We've got x minus 4 squared plus 16 equals 0. Well, we can write 16 as negative 16i squared. And then we get a difference of squares. So now we can write it as x minus 4 minus 4i times x minus 4 plus 4i equals 0. So our two solutions will be x equals 4 plus 4i and 4 minus 4i. Again, we've been able to get our two solutions. And in this case, again, they are unreal solutions. So what we've been able to do here is solve quadratic equations which previously we would have been unable to solve. We have been able to satisfy the fundamental theorem of algebra by finding complex solutions to quadratic equations. Just looking at these two solutions, is there a pattern you can notice? We've got minus 1 plus 2 root 2i and minus 1 minus 2 root 2i. Then we've got 4 plus 4i and 4 minus 4i. Do you notice how the imaginary terms are always the negative of each other? Let's try again in E and see if this trend continues. In this case, we will use the quadratic formula again. So x equals 2 plus or minus the square root of negative 2 squared minus 4 times 4 times 8 all over 2 times 4, which is equal to 2 plus or minus the square root of negative 124 all over 8. And that is equal to 2 plus or minus 2 root 31i over 8, which is equal to 1 over 4 plus or minus root 31i over 4. Again, we have this trend appearing. So the imaginary terms in all three of these complex solutions have been the negative of each other. As I leave you for this lesson, I want you to ponder over this. Can you find any cases where this is untrue? This phenomenon is something which we will be expanding on in the coming lessons. Thank you for watching this lesson. If you have any questions, please leave them below.